So in this video segment and the next, we are going to finally complete the construction of Maxwell's equations, the foundations of all of electricity and magnetism, all of 802 and much, much, much more. We began the course by talking about how these equations attributed to Maxwell describe so much of natural phenomena, so much of nature, and so much of modern technology. And we're almost there in terms of building them up. We've built them up slowly, piece by piece by piece. We're almost there. We have these 4 equations, but we're not quite there yet. There's something wrong. So what are the 4 equations we have? We have Gauss's law, and then we have the magnetic Gauss's law. So Gauss's law tells us how charges make electric fields. Magnetic Gauss's law tells us that there are no isolated magnetic charges. Magnetic fields aren't made by isolated magnetic charges. Then we have Faraday's law. Faraday's law tells us that a time-varying magnetic field makes an electric field. And then we have Ampere's law as we've seen it so far. And you saw when we introduced Ampere's law, we told you that there's something missing. And that's what we want to focus on in this video. I want to figure out what is missing in Ampere's law. And when we add the missing piece, we're going to rename it the Ampere-Maxwell equation, because this missing piece was figured out by Maxwell. But we should start by understanding what's wrong. There's something, in fact, deeply sick about these equations as they are right now. Ampere's law, as we've introduced this, tells us that currents make magnetic fields. What could be wrong with that? I want to show you, actually, that if you've been thinking about this in the right way, stuff that you've learned up to this point from these equations as written here leads to a deep inconsistency. So that's what we're going to do next. We're going to see what's sick about these equations and then figure out how to fix them. So to see what's sick about Ampere's law as you've learned it so far, we're going to use a very, very simple physical setup, something which we've discussed many, many times. We're going to have a current carrying wire. So here's a wire. It's carrying a current I. And this current is flowing into one plate of a capacitor. And here's the other plate of the capacitors. And here's a wire coming out of the other side of the capacitor carrying this current I further along. So this is a perfectly straightforward, completely legitimate, no trickery here, perfectly legitimate physical setup where I have a current charging up a capacitor. The charge on this capacitor is increasing with time as the current carries positive charge into this plate, takes positive charge out of that plate. This plate is becoming positively charged. This plate is becoming negatively charged. And what could be wrong? Well, until this moment, we never tried applying Ampere's law to this setup. This is a perfectly fine setup. We know how to describe the current on the plate. We know, by the way, I'll mention now, we know that there is an electric field in here. So there's an electric field like this. We know that there is a charge plus Q on here, and there's a charge minus Q on here. And we know that Q and E are increasing with time. We're charging up this capacitor. So what we're going to do now is something that you could have thought of doing before that we didn't discuss with you until this moment. Let's try and see what Ampere's law tells us in this setting. So let's remind ourselves what Ampere's law is. And see whether we can apply it to this situation where we're charging up a capacitor. So Ampere's law, as we've learned it so far, says that you can pick any contour or loop or path, closed path P, and do the integral of B dot ds. And what you will get will be mu naught times the current I enclosed by this loop. So I want to pick a path P now, and I'm going to pick a path P that encircles the wire carrying this current. So here we go. Here's my path P, encircling that wire, and I'll label this path P, and I'm going to do my integral of B dot ds around the path in that direction. There we go. I've got a loop like this. And now I want to ask, what's mu naught times I enclosed? Well, let's remember what we mean by I enclosed. By I enclosed, we mean, it's kind of obvious here, right? It's the current going through there. That must be what we mean. But let's remember in equations what we mean by I enclosed. We do a surface integral over a surface S of the current density dotted with unit normal dA. This is our definition. We're integrating the current density flowing through this loop to add up the current enclosed by the loop. And remember that S is a surface bounded by the path P. So now we see that in this situation, we actually have an ambiguity. Because if S is a surface bounded by P, well, kind of the obvious S to choose is this sort of disk, which I'll shade here in green. So if I choose S1, so S1 is this disk. If I choose S1, then if I choose the surface S1, then I enclosed is just I, the current carried by the wire, because where is there a current density flowing through this disk S1? It's where the wire is. So the I enclosed is just I. But I can be perverse and choose a different surface, also bounded by the same path P. If I choose this sort of bag-shaped surface here, so this is a surface S2 that does not just make a disk here. This is my surface S2. This surface S2 is bounded by the same path here, but the surface comes off this path and perversely goes through the center of the capacitor here. And so there's no wire crossing this surface anywhere. Okay, so you got to make sure you understand the picture. I've got a loop here, and I've got a surface that's bounded by this loop, and this surface comes off the loop like this, and then closes here instead of closing right there. It closes here. So if I look at this surface S2, and I work out what is I enclosed, well, it's 0. So there is an inconsistency here. Ampere's law, as we've learned it, is ambiguous in this context. We don't know whether the I enclosed by this path P is 0 or it's I. Which is it? This is the inconsistency. This is the sickness of Ampere's law as you've seen it so far. And this is what Maxwell figured out how to fix. So how are we going to fix this? How did Maxwell fix this? So we look at this equation, and we see that the issue here is that here, if I draw the surface S1, there's a current going through it. Now, what's special about the surface S2? Well, there's no current going through it, but there is this electric field. And this electric field is changing in time. So there's no way of actually deriving what Maxwell figured out. It, in fact, ultimately it flows from testing the final equation against many, many, many different kinds of experiments. But I'm going to give you sort of an extended motivation for the way Maxwell completed Ampere's law. So what Maxwell did was to realize that there must be some new term that goes here. There has to be a fill in the blank right there. And whatever we put here has to have the units of current. Okay, so if I put something in here, it's got to have the same units as this. So it's going to be something with the units of current. But whatever this thing is has to be non-zero on surface S2 and 0 on surface S1. And then I enclosed, so that it will balance out, so that I enclosed, which we're familiar with, is non-zero on surface S1, but then it's 0 on S2. So we have this ambiguity. So if I can put a new thing in here, so what's going to go in here? It's got to be something with the units of current, something which is not 0 on S2, and that strongly suggests that it should be something that relates to the time-varying electric field. So what's special about this surface S2 is that it goes through a region where there is a time-varying electric field here. So I need to write something here that is the units of current. It should depend on dE dt, and it should, if it's proportional to dE dt, then it will automatically have the feature that it's 0 for the surface S1, because on the surface S1 there's no time-varying electric field. So let's think about how we might find such a quantity. And the way to think about this is to start by thinking about the electric field, the strength of the electric field, which is varying with time. So what is the electric field in a parallel plate capacitor? Remembering back to much earlier in 802, the electric field in the capacitor, in a parallel plate capacitor, is Q divided by epsilon naught times the area. This is the area of the parallel plates. And this is increasing in time. This is increasing in time. The area is a constant. If I rewrite this as Q, in terms of Q, so Q therefore is epsilon naught, the magnitude of the electric field times the area. And, well, I'm just pushing symbols around at this point. It may not be clear to you where I'm going, but to see why I did this, the next thing I'm going to do is I'm going to see what dq dt is. And now dq dt, what's changing in time here? Well, epsilon naught and A are not changing in time, but the electric field is changing in time. So this is d by dt of the magnitude of the electric field. And now let's look at what we have. Well, first of all, what's dq dt? dq dt, the change in the charge on this plate per unit time, that's just the current flowing in. So this dq dt is the same as this I, which starts to sound interesting. Because remember, when I put I enclosed here, I enclosed, if I use surface S1, I enclosed turned out to be I. So it's kind of interesting that here I've got something which came from these plates, and this dq dt is equal to this I. So this suggests that I'm going in a good direction. And I can rewrite this as epsilon naught times what? Well, what's A times E? Because the electric field is perpendicular to this surface, A times E is the electric flux through the surface S2, or the part of the surface S2 that goes between the plates here. So this is epsilon naught times d by dt of not the magnetic flux, but the electric flux. The electric flux, which is the quantity that occurs in Gauss's law, which we were introduced to way, way back at the beginning of 802. So now I have all the pieces. I am going to define a new quantity called IDIS. And my definition for IDIS is going to be it's epsilon naught times d by dt of the electric flux. And what you see is that on S2, IDIS, d by dt of the electric flux through the surface S2, that's this quantity, which is this quantity, which is this quantity, which is I. So on S2, if I erase my double exclamation mark here, on the surface S2, I enclosed is 0, but IDIS is equal to I. On S1, what about on S1? Well, on S1, there's no electric fields anywhere around here. So on S1, IDIS is just 0. And now you see what I'm going to do. On on S1, on the surface S1, I enclosed is I dis is 0. On the surface S2, I enclosed is 0, but I dis is I. And so what I'm going to do, and what Maxwell did, was to write I dis here. And as soon as I do that, this is no longer Ampere's law. This is the Ampere-Maxwell law. And in fact, this completes Maxwell's equations. This completes the structure of 802. We're going to discuss this much further in the next video segment, but I want to apologize for one thing here. Why am I calling this I dis? What is dis here? What's this dis? This quantity is called by everybody the displacement current. And I wrote I dis because dis are the first 3 letters in the word displacement. Maxwell was an absolutely magnificent physicist, and he was in fact a great mathematician also. He's responsible for this name because this is what he called this quantity, but I think it's actually a really bad name. But we have to live with it. We don't get it. We don't have any right to rename it, but I don't think it's a good name. Why do I not think it's a good name? Well, displacement. What is this quantity? Well, what this quantity is that it's the integral over this surface of the time variation of the electric flux through the surface. That's what it is. That's what Maxwell said it was. It's nothing to do with displacement of anything. Displacement of who? Displacement of what? It has nothing to do with displacement. It's also not a current. Now, it's true that it has the units of current, so maybe calling it a current is somewhat more justified, but it is not a current. There's no electrons flowing through the surface S2. It's not a current. It has the units of current, but it is not a current. And sadly for us, there's no escaping the fact that we have to call it the displacement current because that's how Maxwell named it. But even though Maxwell was great in so many ways, this choice of name is in fact unfortunate. So that's where we are. In the next video, I'm going to rewrite this equation. We're going to look at it. We're going to understand start to understand what it's telling us. But this, what I've just done for you today, first of all, you should understand why without this term, Ampere's law is sick. And second of all, although what I've done is a pseudo derivation, not a real derivation, this should really motivate for you why this is in fact the right thing to add here to make this a sensible and well-behaved equation. And this in fact was Maxwell's first great discovery, and we'll very soon get to his second.